Yeah, let's start the afternoon session. So we are very happy to have Shreya Vardhan talking about entanglement dynamics from universal low-lying modes. Shreya.
Okay, great. Thanks a lot to the organizers for putting together this really excellent conference and for the opportunity to speak. So I'm going to be talking about this recent paper with Sanjay Mudgalia. Okay, so far in the workshop, we've heard about a lot of different applications of entanglement entropy and other entanglement measures in various contexts. And in this talk, we'll be discussing universal properties of the time evolution of entanglement entropy in chaotic quantum many-body systems. Okay? So the reason that we should expect that there are such universal properties is because of a general feature of chaotic quantum many-body systems called thermalization. So suppose we start with some initial state rho 0 in our system and evolve it with the many-body Hamiltonian H. Then if H is chaotic, we expect quite universally that at late times, most details of rho 0 will be forgotten, and rho of T will resemble a thermal density matrix, rho equilibrium at late times. Okay, and this process happens essentially independently of the microscopic details of the system, even though the mechanism for it is not fully well understood. It's been observed quite ubiquitously. Okay, and one reason why we should be interested in this process in this workshop is that holographic CFTs are one example of highly chaotic systems, and thermalization in the CFT in this context corresponds to the process of black hole formation in the bulk. So understanding the microscopic mechanism for thermalization on the boundary will shed some light on understanding the microscopic mechanism for black hole formation in the bulk. Okay, so if we have a chaotic system with local interactions, then we expect that as time evolves, increasingly large regions become thermalized, as shown in this picture. And so in particular, if we consider any fixed region A, say some region smaller than half of the system, then if we look at the reduced density matrix rho A of T in that subsystem, we expect that it should approach a thermal density matrix at late enough times. And one way to prove that this is happening is to look at the time evolution of the Renyi entropies, which have been discussed a lot so far in the workshop. They're defined in this way in terms of the reduced density matrix of the time evolved state of A. In particular, the n going to 1 limit of this quantity is the von Neumann entropy, which has the best operational interpretation, but the higher Renyis also shed some light on the structure of the state. Okay, so due to the process of thermalization, we expect that these quantities at very late times will approach some extensive thermal value for any system. So at late enough times, we'll have that the value of this quantity is given by some proportionality factor, which is of order 1 times the volume of the system. Okay. In fact, we expect that there is universal behavior not only in this late time saturation value, but also in the way in which it is approached. And this is true, we're familiar with this in the context of correlation functions, such as 2-point functions and higher point functions, where we expect that the late time evolution is governed by hydrodynamic modes. For the entanglement entropy, it's hard to study the evolution analytically in general chaotic time evolutions, but there are a few analytically tractable examples. And by looking at them, we seem to see a remarkable universality. Okay, so in particular, if we look at two very different systems, one is a random unitary circuit, which is a type of spin chain system where we couple adjacent sites with a sort of maximally random unitary, and then evolve with some discrete time evolution. And on the other hand, we consider a holographic CFT, which is a continuum theory with a fixed set of couplings. In these two very different contexts, we find that we can express the evolution of the entanglement entropy at late times in terms of a common expression known as the so-called membrane formula. Okay, based on these calculations, it was conjectured to hold universally in this paper of Johanna, Hughes, and Nehum. So let me introduce briefly what this formula is. So let me state it for the case of one spatial dimension. Suppose we want to find the nth Renyi entropy to the left of some point x in the system as a function of time. So the prescription of Johanna, Hughes, and Nehum is that we should extend the system in the time direction, in some auxiliary time from tau equal to 0 to tau equal to t. And then in this slab, we should consider all possible lines with different velocities going through it. And then the time evolution of the nth Renyi entropy is given by considering for each such line a sum of two terms. The first term has a contribution which is linear in time and involves some non-trivial function of this velocity. And then the second term is some initial entropy contribution from the region to the left of this endpoint y. Yeah, we can assume that it's infinite for most purposes. We can also consider the case where it's finite but large.
I see, but can we consider a case where it's finite, but the subregion we're looking at is more than half the system, or that's not?
Yeah, this formula would apply even for initial mixed states, for instance. So it's quite general.
So you give us the page curve.
Yeah, if you consider a pure state, then it would give you the page curve because the saturation value will be determined by certain curves which go to the endpoints of the system in two different ways, and then that gives you this minimization in the page curve. Okay, but if we're considering the case of the infinite system, then we just need to consider different straight lines reaching the bottom boundary. And we have the sum of two terms. One is explicitly linear in time. The other one involves an initial entropy contribution. And we minimize overall velocities.
Sorry, SEQ is the equilibrium value of
the equilibrium density of the entropy. Yep. Okay, and in particular, this function is model dependent, but it has some universal features. So it generally has a shape of this kind. And in particular, it obeys certain constraints. So if this dotted line is the 45-degree line, and there's a constraint that this curve should always touch that line at a single point. And I'll explain what that means in a second. Okay, but so there's some formula like this, and we can try to, this is just a repetition of that from the previous slide. And we can consider how it affects the evolution of different initial states. Okay, so suppose we consider a family of initial states which have volume law entanglement entropy at t equal to 0 with some volume law coefficient s. Okay, so if I'm considering the entropy of the region to the left of y, then I have the volume of y times some number s, which can be between 0 and the equilibrium density. And once I plug this initial entropy formula into this expression, then if I just consider the case of a product state, then this term would just not be present at all. And then I would just pick the value of this membrane tension function at b equal to 0. Okay, but then if I have a more general initial state, then I get some other growth rate, which I'll call gamma of s, which is related to this membrane tension function by Legendre transform. And in particular, if I started with the equilibrium state already, then that state just doesn't evolve. So I should find that its entropy doesn't grow. And so this gamma of s should be equal to 0 when s is equal to s equilibrium. Okay, and that is what is being encoded in this constraint that this membrane tension has to touch this line at some velocity. Okay, so there are some natural consequences of this formula, which you expect from thermalization. And it turns out to hold in these two very different kinds of systems, but the methods that are used to derive it in these two different systems are very different from each other. So in particular, the random unitary circuits, we use certain averages for random unitary matrices, and we can do very explicit calculations for the second Renyi entropy, and then there are results in certain limits if you consider the third Renyi entropy. On the other hand, in holographic CFTs, we use the fact that thermalization in the boundary is dual to gravitational collapse in the bulk. And then to find the time evolution of the entropy of some subsystem, these authors applied the HRT formula, which has been discussed a few times, in order to find the evolution of the von Neumann entropy. And this calculation can be further simplified in a limit where the system size, the subsystem size is large, and we consider late times. And in this case, we can completely get rid of the radial direction of the HRT formula in the bulk. And we can just reduce that formula to a minimization problem just in the boundary, which has exactly this membrane form. Okay, so in particular, the membrane tension that we get from this is a different function from the random circuit case, but it satisfies some the same non-trivial constraints that I mentioned. Okay, so because these derivations are so different from each other, but the formula appears to be universal, we can ask, what is the physical meaning of this entanglement membrane, and where is this universality coming from? And very heuristically, we might think that if the state is being prepared by some kind of tensor network, then the membrane is a minimal cut through the tensor network. But in order to actually understand this structure, we should address the following more precise questions. So firstly, we can ask, what is the source of the velocity dependence of this function epsilon of v? What does that mean? And we can also ask, so we have some understanding of hydrodynamics of correlation functions in terms of certain low-lying hydrodynamic modes. So is there some analogous structure for the evolution of the entropy? And in particular, does this arise universally in very different kinds of systems, including holographic CFTs? And we can also ask about the dependence of this epsilon of v function on the Renyi index n and how the structure changes as a function of n.
So this picture that you had
It's supposed to be the boundary time, but we're considering the boundary time from t equal to 0 to t equal to t. Yeah, but it's just the region in the middle doesn't have any very clear interpretation other than you just consider different lines of different velocities and integrate this function. Okay, great. So these are the kinds of questions we would like to address. In this talk, we'll propose a common underlying structure, which will involve certain low-lying modes. And in order to do this, I'll make use of a concrete set of models, which involve time-dependent Hamiltonians, where I fix some set of local couplings, H alpha, and then I make the coupling coefficients, which appear next to them, some random functions of time and some random variables, which are uncorrelated for different alphas. Okay, so the advantage of doing this is that because of this time-dependent randomness, these models will turn out to be simple to treat analytically, relatively simple to treat analytically. But at the same time, they're not quite as random circuits because we fix the couplings. And also we can tune various microscopic parameters by tuning these couplings. Okay, so then we can ask about the extent to which the membrane picture is universal as we vary the different couplings. Okay. And previously, one reason to expect that the lessons that we would learn from this set of models might be more general is that they've previously been used to understand diffusion in two-point functions and to give a very explicit derivation of the hydrodynamic modes that lead to diffusion. So we can try to identify what are the analogous modes for entanglement growth. Okay, so the key simplification that happens in this set of models is that observables that we're interested in, like the nth Renyi entropy, can be rewritten as so they can always be rewritten in terms of some Euclidean evolution on 2n copies of the system. But in this set of models, this Lorentzian evolution on 2n copies can be mapped to a Euclidean evolution on 2n copies. And that significantly simplifies the discussion. So if you look more closely at the expression for the time-evolved nth Renyi entropy, you can see that it has n factors of u and n factors of u dagger appearing in it. And this can be given a representation on some Schwinger-Keldysh contour with n time folds, like this. And so the relevant object is u times u star raised to the power of n. Okay, and the simplification that happens is that we can map this entire object after averaging over the random couplings that I showed to some e to the minus p2nt for some Euclidean Hamiltonian p2n, which lives on all of these copies. Okay, so let me very briefly discuss how we end up mapping this Lorentzian evolution to a Euclidean evolution. And let's just discuss the case of n equal to 1, where you have u and u star. Okay, so this is just saying again that the Hamiltonian has this form of a time-dependent Hamiltonian with these j alphas. And the average of each j alpha by itself is 0, and the average of product of two of them has this form, where in particular we've introduced some discretization of the time step, where we say that the time evolves in steps of size epsilon, and then this is a discretization of the delta function. Okay, so then let's consider u times u star for some small time interval epsilon. And let's label the two copies of the system A and B, and just expand this for small epsilon, so we get a set of terms like this. And then we want to collect the terms with different powers of epsilon in this expression. So first we just get 1, and then the linear term in the h's vanishes because of this vanishing of the average of j. So then we collect the quadratic terms, but because the variance is proportional to 1 over epsilon, we end up getting something with this structure, where we get 1 minus epsilon times this operator p2, which is a sum of non-negative terms, which involve the h alpha operators on both the copies A and B. Okay, and then there will be some natural generalization of this for higher n's. Okay, so let me just summarize the results before going into details. So, so far we found that the nth Renyi entropy can be expressed as a transition amplitude under Euclidean evolution with a non-negative Hamiltonian p2n. And so now that we have a Euclidean evolution, if we want to find the behavior at very late times, we just need to understand the behavior of the zero energy subspace of this Hamiltonian. Okay, so we can work out for general choices of these H alpha couplings, what is the structure of the ground state subspace, and we can construct the projector onto it. And from that, we get an equilibrium value, which is consistent with what we expect in general from thermalization, as was discussed earlier in this paper. Okay, but now in order to understand the approach to equilibrium, we need to understand the structure of the low energy eigenstates. Okay, and it turns out that these also have a universal structure. So in particular, if we consider, if we choose these H alpha couplings to be such that they don't commute with anything except the identity operator, so there are no additional symmetries of the time evolution, In that case, we find that this P4 has just 2 degenerate ground states, and these can be written as products of certain spin variables between different sites. So either you get a product of all downspins between different sites or all upspins between different sites. And these ups and downs are related to the permutation degrees of freedom that Pratik introduced in his talk. So essentially, they're related to the 2 permutations in S2. The upspins can be seen as being related to the identity permutation, and the downspins are related to the swap permutation. And for higher n's, we'll get a generalization of the structure where we have n factorial different kinds of spins. Okay, these are the ground states, and then it turns out that the low energy eigenstates have a universal structure where they consist of plane waves of domain walls between these down and up spins. Okay, so we have a sum over x of e to the I kx times states which have downs up to some location x, and then the domain walls can be locally dressed with some other degrees of freedom for some order 1 number of sites d in the thermodynamic limit, and then we have all up spins. Okay, so this is the general structure of the low-lying eigenstates in the set of models, and this structure, as I'll show, leads to the membrane picture. In particular, these one-particle excitations have some dispersion relation, E of k, which is gapped. And this dispersion relation is related to the membrane tension and to this growth, entropy growth rate as a function of the initial entropy density. Okay, so in particular, I mentioned that if you have different initial states with different initial entropy density, then the growth rate depends on what that initial entropy density is. And it's just related to the dispersion relation evaluated at some imaginary value of momentum equal to I times the initial entropy density. Okay, and then you can also give some explicit expression for the membrane tension as the Legendre transform of this object. Okay, so if we think of these modes as some analog of hydrodynamic modes for entanglement, then they're unconventional in a few different ways. So one is that the dispersion relation is gapped. And then even above the gap, it turns out that we need to, that the order 1 values of momentum are actually important. And in particular, they'll turn out to be important for satisfying the constraints on the membrane tension that I mentioned earlier. But apparently, yeah.
Sorry, Shreya, I'm not using the thread. So just to ask you, so you have this domain wall, and is the tension of the domain wall the tension of E of V? I mean, you had a domain wall at the start of your talk also, or
yeah.
Sets of, are they the same or they are different?
Yeah, they're very closely related. So this dispersion relation is related to the membrane tension in some direct way, which will come up in a couple of slides. Yeah. Mm-hmm.
So this membrane tension is n-dependent, or it's like
it is n-dependent. So I'll discuss the n-dependence. So the discussion that I have so far is just for the case of the second Renyi entropy. And then it'll turn out that if I'll also consider the case of the third Renyi entropy. And in that case, we'll have some analogous set of low energy eigenstates. But then it'll turn out that they actually have some non-trivial competition with another set of eigenstates, which are not of this form. And that will lead to some phase transition in this membrane tension as a function of velocity. So there are some qualitative differences between the n equal to 2 and higher n cases. Okay, so good. So the plan for the rest of the talk is to first introduce more explicitly the expression for the second Renyi entropy as a transition amplitude, and to give the definitions of these up and down spins more clearly. And then I'll derive the low energy excitations that I mentioned on the previous slide very explicitly in a simple limit. And then I'll discuss how the structure remains robust more generally and what changes in the case of the third Renyi entropy. Okay, so let me introduce the expression for the second Renyi entropy as a transition amplitude. So again, the explicit expression is given in this way, and I have 2 u's in this expression, which I'll say live on copies A and C of the system, and 2 u daggers, which are associated with backward evolution, which live on B and D. Okay, and then the spin variables that I'll introduce also live on 4 copies of the system. And the upspin is a maximally entangled, and I can associate these spin variables with 4 copies of a single site of the system. Okay, so the upspin consists of a product of a maximally entangled state between the A and B copies times a maximally entangled state between the C and D copies. And the downspin is a maximally entangled state between A and D and B and C. Okay, and then the evolution of the second Renyi entropy is given by this expression. where the initial state is related to the actual initial state of the system. And then we have this time evolution operator. And then the final state is a domain wall between these down and up spins. So we have down spins in the region A and up spins in the complement of A. The state is in 4 copies. Everything here is in 4 copies of the Hilbert space. Yeah. Okay, and because we want to consider the most general initial states and consider some universal properties of this evolution, we'll consider the backward evolution of this domain wall state under u times u star squared in this discussion. Okay, we can see that the P4 Hamiltonian generically has these 2 zero energy eigenstates, which are all ups or all downs. And once we substitute the projector onto that ground state subspace into this expression, we immediately end up with the page value for the entropy of a pure state evolved to late times at infinite temperature. So we get this minimization between log of dA and log of dA bar. And now we would like to understand how this value is approached using the low energy modes. So in order to understand this, we'll first consider an even simpler system where we don't allow sort of fixed couplings H alpha, but just take the H alphas themselves to be random matrices drawn from the GUE ensemble. Okay, and the Hilbert space dimension at each side is Q for a single copy of the system. And now again, we can repeat the analysis that I described and derive some P4 Hamiltonian for the evolution on 4 copies of the system. And the advantage of using this completely random case is that in this case, P4 will be expressed entirely in terms of the up and down spins, and the same up and down spins which appeared in the boundary conditions for the entropy. Okay, so now we can further take a large Q limit where the local Hilbert space dimension is large. And in this case, we can consider the evolution of this domain wall state with down spins up to some x and then up spins after that. Okay? And we see that P4 has a very simple action on the state where either it keeps the domain wall at the same location, or with a factor of 1 over Q, it moves it 1 step to the left or 1 step to the right. And then this action is very easy to diagonalize, and we can immediately see that the relevant eigenstates consist of plane waves of these domain walls. So in this case, the statement that I mentioned on the first slide is just exact, that this is the form of the eigenstates. We can also work out the dispersion relation, and that just has this form, which can be represented in this way. So there is some gap above the zero energy eigenstates, and then you have some dispersion of this kind. Okay, so let's see what this implies for the evolution of the second Renyi entropy. So we return to this expression as a transition amplitude. And if we're finding the entropy to the left of some region y, then this is the final state. And we can, and in this large Q limit, this single domain wall state just evolves to single domain wall states at other locations. Okay, so we can insert a resolution of the identity here for domain walls at other locations. And then we can identify this second factor appearing here as just the initial entropy up to x of the initial state rho 0. Okay, so we get a sum over different locations x that this domain wall has gone to, and then we get a factor of e to the minus s for the initial entropy, and then this domain wall propagator. And then into this, we can insert the structure of the eigenstates that I mentioned on the previous slide. And from doing that, we get some simple expression, which is just the Fourier transform of e to the minus e of k times t. Okay, and by analyzing this expression in the late time limit, and also substituting it into the sum over x on the previous slide, we end up just with a minimization over different velocities of the associated with the final location of the domain wall. And this kind of general formula, which is exactly of the membrane form that I mentioned before. And in particular, the membrane tension turns out to be related to the dispersion relation by this equation. So we evaluate the dispersion relation at some imaginary value determined by the saddle point equation. And we end up with some function epsilon of v. Okay.
Just to understand this,
yeah.
So the idea is you start with the region to the left of where the blue line ends.
Yeah.
And you know, that's the density matrix of interest at time t equal to 0. At time t equal to tau or whatever, you're interested in the corresponding region shown to the left of the endpoint.
Yeah, so this is the region for, so the region to the left of this is the region for which I wanted to find the entropy at time t.
Okay, you're starting there.
And then I consider all possible initial regions.
All such that, and then there's some chosen value of v, is it?
So the value of V that ends up contributing depends on whatever comes out of this minimization. So the minimization over V is coming from the fact that in this expression I had a sum over X. So, and then this whole thing will end up being something which depends in an exponential way on time. So at late times, I just want to pick the largest contribution. Yeah, so, right. So it just comes from, essentially all of this structure is coming from taking a late time limit. Okay, and then we can also consider the setup where you consider an initial state with volume law entropy with different coefficients S. And the growth rate can be seen as directly related to this dispersion relation evaluated at I times S. Okay, so this was how the structure of this membrane picture came out of the low energy modes in this very special case where I first took a completely random time evolution and then further took a large Q limit in it. And now I want to see how it's robust more generally. So the first thing I'm going to do is still consider these random matrices, but now consider finite Q. Okay, so what happens at finite Q is that the domain wall doesn't remain a single domain wall at later times, but it can now split into multiple domain walls with some factor of 1 over Q squared. And in principle, I could consider perturbation theory with this additional term, but since I just have some spin 1/2 system for my effective Hamiltonian, I should just directly diagonalize it and see what I get. Okay, so in doing that, when I numerically diagonalize P4 for different values of Q, I can obtain the momentum resolved dispersion relations. And they have these forms for different Qs. So one thing that we can check is that the spectrum still has a gap for any finite value of Q. Okay, so all of these lowest values are bigger than 0. And that implies that if I started with an initial product state, then the entropy growth rate would be non-zero. Okay, so that is a good first thing that remains robust. But then I need to understand further if the structure of the eigenstates of the lowest band in these cases is robust. So what is being plotted here is just all the low energy eigenstates for a given momentum. So we can see in the Q equal to 3 and Q equal to 4 case, there's some gap between some well-defined single particle band and some multi-particle continuum of states. Okay, but then what happens in the Q equal to 2 case is that at small k, you still have some well-defined one particle band, but it's not clear what is happening at larger values of momentum and whether there is any robust notion of a one particle band in this case. Okay, so we would like to understand both of these questions, whether in this case, the one particle band has some robust structure of the eigenstates, which still looks like the large Q limit, and in the Q equal to 2 case, whether you can even have anything like a one particle band. Okay, so in order to address this, we'll use the following strategy. We'll consider variational ansatz for the eigenstates, where we assume that they have this form that I wrote on the first slide. So you consider states which are plane waves, so states with downs up to some x, and then some order 1 region of delta sites where I can have any combination of up and down spins. And then beyond that, I have all up spins. So what this means is that I can have, in this set of trial states, I can have as many additional domain walls as I can fit into delta sites. Okay? What we can do is we can consider different values of delta, and in each delta, we can minimize this expectation value of P4 in this state. Okay, so this can be done by some explicit numerical procedure where we end up with a problem of diagonalizing an effective Hamiltonian which just lives on a 2 to the delta dimensional Hilbert space for each momentum. Okay, and then we can do this procedure for different values of delta. And if we find that as we do this and increase delta, the dispersion relation is not changing very much, then that is telling me that these eigenstates are actually a good approximation to the actual eigenstates of the system. And the dispersion relation that I'm getting from this procedure is a good approximation to the actual dispersion relation. Okay, so this is a standard technique which is used in the condensed matter literature for probing low energy excitations and was used in particular by this set of authors. Okay, so when I apply this to my effective Hamiltonian for Q equal to 3, where I did have a well-separated one particle band, then as I look at the dispersion relations for different deltas, I find that indeed it's changing very little as I increase delta. So that confirms that the eigenstates do have the structure of a locally dressed domain wall. And I can check this more explicitly by looking at different values of k and plotting the differences between the energies that I get as I increase delta. Okay, so this indicates that there is a roughly exponential convergence of the dispersion relation with delta. And I can also compare these variationally obtained dispersion relations to the results that I earlier got from exact diagonalization, and I see that this sits right on top of the one particle band that I obtained from exact diagonalization. Okay. So that was the q equal to 3 case where I did have a well-separated band, but now I can consider also the q equal to 2 case using the same method. And I find that the initial increases in delta do change the dispersion relation, but there is almost no change between delta equal to 3 and delta equal to 4. Okay, so again, this confirms that in the q equal to 2 case, I continue to have a well-defined one particle band, even at high values of momentum, with some order 1 dressing, which is not very important in the thermodynamic limit. Okay, so, and then I can compare the variationally obtained dispersion relation in this case, again, to the result that I had from exact diagonalization. And I find that there is very good agreement for small momenta, and then at large momenta, this one particle band extends into the multi-particle continuum. Okay, and so even though there are other sort of multi-particle excitations which have comparable energies, this one particle band is the only thing which has significant overlap with the final state, the single domain wall state, which appeared in my expression for the time-evolved Renyi entropy. Okay, so the moral of this is that the structure remains essentially unchanged even in the q equal to 2 case, which we should have expected just from the fact that this is still some highly chaotic system just with a lower on-site Hilbert space dimension. Okay, so then again, I can substitute this structure of the eigenstates into my expression for the time-evolved entanglement entropy. And essentially, if I'm considering a limit of large system sizes in late times, then the local dressing with some order 1 delta can be neglected in all of the expressions. And the only thing that changes is that now this membrane tension function is given by the Legendre transform of the modified exact dispersion relation instead of the large Q dispersion relation. Okay, so I can use these numerically obtained dispersion relations and numerically calculate the membrane tension function that I get from them and look at that for different values of Q, and I find that all of them, so these are plots of the membrane tension function for different Qs, and I find that all of them satisfy this constraint that they become tangent to the 45-degree line at some velocity, which I can then identify as the so-called VB. Okay, and then another interesting thing that I can explore is just looking at how the entanglement velocity, which is related to the minimum of this curve, and the butterfly velocity, which is related to where it becomes tangent to the 45-degree line, how both of these velocities behave as a function of Q, and I find that the entanglement velocity actually has an interesting non-monotonic dependence, where it increases up to, say, Q equal to 5 and then starts to decrease, and the entanglement velocity, and the butterfly velocity is just monotonically increasing. Okay, good. So this was still the case where I had taken completely random matrices coupling adjacent sites, but now let me consider a more specialized case where I choose some particular values of my coupling operators, and then the only thing I tune is the strengths of the couplings which appear next to them. Okay, so I take, in order for my system to not have any symmetries, I take the coupling operators to be Zi, Xi, and Zi plus 1, which is like the mixed field Ising model, which is often studied in the context of quantum chaos, except that now this is time dependent. And I take the variances of these different couplings to be proportional to some numbers Gz, Gx, and Gzz. Okay, and I can choose to fix Gx and Gzz to 1, and then see how whether or not the structure remains robust as I consider different values of Gz. Okay, so again, in this case, the structure changes in the following way. So the ground state subspace of P4 in this case is still spanned by the same up and down spins, except in one special case where I set Gz equal to 0, in which case the system is actually not chaotic anymore. But now what changes is that I don't get a closed Hamiltonian just on the subspace of these up and down spins. So I can now, under the action of P4, go into a much larger Hilbert space where I have 2 to the 4 degrees of freedom at each side. Okay, and in this context, I can no longer use exact diagonalization because I have a 16-dimensional Hilbert space at each side. But I can still use the same variational ansatz that I introduced. And now, again, I assume that the eigenstates have this kind of structure with all down spins up to some x, and then all up spins after x plus delta. And then in the intermediate region, this state now has a different interpretation from before, where it can be an arbitrary state in a 16 to the delta dimensional Hilbert space. Okay, and this is associated with the fact that I no longer remain confined to these up and down degrees of freedom. Okay, but so this is a large number, but even because I'm considering this variational approach, I can still consider delta up to say 3 and see what I get from that. And okay, so these are very small labels, but these first two plots are for GZ equal to 1, and it was down up to
from
x.
1 to delta, and then everything else again from delta. It was down and then up, and in the middle there was this batch of delta, which was could be whatever.
It could be anything. And yeah, and then again, I want to fix delta, and then allow all possible states, minimize the energy for all possible choices of the intermediate state, and then see.
Including over this phi.
Yeah, sorry, so the phi is the thing that I'm varying. So say first I fix delta equal to 1, then I just have a 16-dimensional Hilbert space in which I want to find the minimum of the energy, then I consider delta equal to 2, and I get 16 squared, and so on. Okay, and then these are the dispersion relations that I get from carrying out that procedure. So I guess in decreasing order, they're from delta equal to 1 to delta equal to 3, and carried out for different values of gz. Okay, and these values of gz equal to 1.0 or 0.5 are sort of generic cases where we expect the system to be chaotic. And the case where gz is equal to 0 is where the system can actually be mapped to a free fermion system by a Jordan-Wigner transform. So in that case, we expect that the evolution is not chaotic, and we expect the structure to break down. Okay, and that is kind of exactly what we're seeing. So we're seeing pretty good convergence of these dispersion relations at generic values. But in this case, for gz equal to 0, we can sort of see with our eyes that there is less good convergence. Another test that we can do is
Convergence means convergence in delta.
Convergence in delta.
And this is good because it's kind of, you think the orange and the green are kind of converging to each other, but this one is not good because they're separated.
Yeah, even for small momenta, they're pretty well separated. And another check that we can do is that we can calculate the membrane tension that we get from the Legendre transform of this dispersion relation. And that had to satisfy certain constraints. And those constraints are well satisfied for these two cases. So these are the membrane tension curves that you get from gz equal to 1 and gz equal to 0.5. But then in the case for gz equal to 0, so yeah, unfortunately we can't access higher delta than 3 just because of numerical constraints. But the delta equal to 3 curve that you get in this case leads to a membrane tension which does not satisfy the constraints because it's not tangent to this 45-degree line. And that is what we expect because the system is not chaotic, so we expect this whole structure to break down.
So you can't access because there's like some 4096 dimensional space or something?
Yeah, so if we have, yeah, we can access up to
16 into that would be like 64,000, but that's too hard to do.
Yeah, at least on the laptop. But,
You're
yeah.
just doing gradient descent, right, or something in these parameters?
Yeah, so essentially we can make some basis of states for these pies.
Right, and then you do gradient descent in those parameters.
Yeah, you don't even explicitly have to do that. You just sort of write down the equations that you get for minimizing the energy, and that translates to just a Schrodinger equation for some effective Hamiltonian, which is just the actual Hamiltonian projected onto this subspace.
I see. But you could also have just used this as a variational ansatz really and done gradient descent in those parameters. Right now, I thought we can do gradient descent in millions of parameters.
Okay. Yeah, maybe that is something to try, but yeah. But with the method that we used, somehow beyond, like if you consider larger values of delta, then it becomes very hard to do numerically. Maybe it could be done for the delta equal to 4 case, but it would be extremely slow. But yeah, maybe that's worth checking. In any case, so the dispersion relations that we get in this case satisfy the memory tension constraints, so it's unlikely that they would change much further if you increase delta more, because you already get the right curve. But then in this case, it should change more, and yeah, the entanglement velocity probably goes to 0. Okay, so this was all for the case of the second Renyi entropy in a variety of different models. And let me now briefly discuss the case of the higher Renyi entropies.
5 minutes after this.
Oh, okay. So for the case of the higher Renyi entropies, I'll end up using a similar approach, but I'll go back to this Brownian GUE model where I take the matrices with which I couple the different sites to be random matrices. Okay, so what changes in this case is that this final state, this final domain wall state that I had is now no longer a domain wall between the up and down states that I had before, but instead, more generally, it's a domain wall between states associated with the cyclic permutation, which takes n to n minus 1, n minus 1 to n minus 2, and so on, and the identity permutation. So in particular, for the case of n equal to 3, these states have this form where the identity state just couples F1, is the maximally entangled state between F1 and B1, F2 and B2, and so on. And the eta state has this set of pairings. Okay, so that change, that is the sort of kinematical change in the expression for the nth Renyi entropy. And the dynamics are also different. So now this Hamiltonian P6 that I get on 6 copies of the system has, instead of a spin 1/2 Hilbert space at each side, it has an n factorial dimensional Hilbert space at each side. And the relevant state that I'm interested in for the entropy evolution has this domain wall between eta up to x and then identity after that. And that state will now no longer stay restricted to the eta and E subspace, but it'll go into a subspace involving all the other permutations in Sn. Okay, so again, this is not tractable to diagonalize numerically because even in the n equal to 3 case, I have a 6-dimensional Hilbert space at each side, so I can't go to any reasonable system size. But I can again make use of the same variational approach that I discussed before, and I can test whether a state of this kind, which has domain walls between etas and e's with some order 1 dressing in between, which can involve other permutations, is a good eigenstate or not. Okay, so I carry out the same procedure. So now I allow this local dressing state phi to be an arbitrary state in an n factorial to the delta dimensional Hilbert space. And for n equal to 3, I can use this method up to delta equal to 4. And then from doing that, again, I get pretty convincing results that the dispersion relation is converging with delta, and the convergence is faster as I increase q to larger values.
So number question is phi is, I should have asked earlier, phi is not normalized, right? So the coefficient of e to the ikx just goes into phi.
Yeah, so I should, I've not written them in a normalized form, but of course, when I'm actually carrying out the variation procedure, I should use normalized states.
Then you should also put a c number in front of e to the ikx when you sum over x.
Yeah, so in principle, I should have that. But yeah, the reason that I'm not including that is that when I eventually plug into the expression for the entropy, then I'm only interested in the exponential part of that expression in this limit of late times and large system sizes. So then this prefactor that you get from this coefficient will not end up making a difference. Yeah, so all of these simplifications again happen because of the scaling limit. Okay, so this numerical procedure again shows me that this is a good approximation to my eigenstates. And again, I can plug in the expression, the eigenstates into the evolution of the entropy. So in particular, I can consider an initial state with entropy density S, and I can do the saddle point in this integral. And I end up now with some generalization of the formula that I had before, where I insert n minus 1s in various places. Okay, but from doing this, I can find the growth rate of the third Renyi entropy as a function of the initial entropy density. And okay, so now I can use the dispersion relation that I obtained on the previous slide numerically and plug in into that this value of k. And the growth rate that I get from that is this blue curve. Okay, and for comparison, the thing that I get from the second Renyi entropy for the same case is this curve. And we can immediately see that there is a problem with the blue curve that I get for the third Renyi entropy, which is that unlike in the second Renyi entropy case, where the growth rate is going to 0 for the initial equilibrium state, this third Renyi entropy curve has some large non-zero value at s equal to s equilibrium. Okay, so this dispersion relation that I'm getting, and once I find the growth rate from that, is violating the condition that the entropy of the initial state should not grow at all, which is a very important condition and should not be violated. So the only way to fix that is if, in addition to these contributions to e to the minus n minus 1s from this particular set of eigenstates, I also have other contributions from a different set of eigenstates which can compete with them. Okay, and then we can propose a natural set of other eigenstates, which I won't go into the details, but from those we end up with an expression for e to the minus 2s, which is a sum of two terms. So one involves this naive growth rate that I get from the third Renyi dispersion relation, and the second term involves the second Renyi dispersion relation. Okay, and from the sum of these two terms, the actual growth rate is given by the minimum of the growth rate for the third Renyi entropy from the naive dispersion relation and the growth rate for the second Renyi entropy. Okay, so it's the minimum of these two curves. So in particular, I seem to be learning that beyond some value of s, the two growth rates become equal to each other for the second and third Renyi entropy. Yeah, and there is some first order phase transition in this growth rate, which maps to a first order phase transition in the membrane tension. So I'll just leave it at that. Yeah, maybe just leave the final questions.
Do you have any holographic interpretation for this, like what this domain wall means?
Yeah, so that is something that we're trying to understand. So the only holographic calculations that has been done is for the von Neumann entropy, where the domain wall is not very transparent because you don't explicitly have n copies of the system. So somehow we would need to do a calculation for the evolution of the second Renyi entropy and the third Renyi entropy and so on. And that involves sort of a prescription, as you discussed, where you have to consider a back-reacted geometry from this cosmic brain. So that is something that we're looking into now with Mark Mazet and Zhencheng Wang, but we expect that some structure like this should come from that calculation.
But the domain wall is not just the cosmic brain, right? Like the leading answer that you got was like the RT type formula, which was just from this max state. Mm-hmm. This domain wall is something else, right? It's like
the domain wall is somehow, so it's related to the boundary condition for the nth Renyi entropy, and it's somehow related to how that boundary condition propagates in time.
Okay.
I'm not sure exactly how that structure would
come out. Later. Yeah.
Yep.
Sorry, I apologize that I followed the talk so poorly, but let me just try to see if I got the basic point right. So let's say you start with your final time slice on that picture where you, and you were trying to compute, let's say, trace rho square in that simplest case for some region on that late time slice, right? Yeah. And then you had this minimization procedure or whatever. You had these different velocities. Yeah. And those lines intersected the initial time slice in various regions, right? Yeah. And then you had these domain walls. And so was the idea that to compute the final value of trace rho square in that region of interest, you basically have to start with the domain wall with its flip point being located where the line for the minimum value hits the initial time slice, and then let that propagate in some way? Was that the picture?
Right, so the picture that we're considering, do you agree with this expression that this is the evolution, this is the expression that you get for the evolution of the nth Renyi entropy? So you have some initial state which depends on the actual initial state, and this domain wall is essentially sort of encoding the pattern of traces in the nth Renyi entropy. Okay, so the fact that you have down states corresponds to having a particular identification of the different copies, and up states correspond to a different. And then, so this is our expression, and there is some Euclidean evolution. Now we want to consider the backward evolution of this domain wall.
That slide where you had the lines drawn for different velocities.
Yeah.
In the initial, So now what? So let's say I thought you were trying to compute trace rho square upstairs at tau equal to 2.
That's right.
And then what do you do at the bottom to get there? That is, I take it that you have some domain wall moving at velocity v.
Yeah.
Which hits there, but what is the initial state you're starting with?
So the initial state could be anything. Okay, let's go back to this expression. So here, in this expression, I insert, because if I just consider the evolution of the domain wall, so I forget about the initial state, then the domain wall can move to various other locations. Okay, so then in this expression, at the final time, I can insert some resolution of the identity. Okay, so that resolution of the identity is just dx. So then I get two factors. One is telling me about the propagation of the domain wall from y to x. And then the second factor, if you just look at this expression at t equal to 0, okay, this corresponds to the initial e to the minus s2 at t equal to 0, but now at this other location x. Okay, and in this expression, we have a sum over all possible x's.
I see, okay, I understand, I see. And the final answer was that rho square, I mean, if you went back in time, what became smaller or grew or whatever linearly in time with a velocity that was not quite the domain wall velocity? Or was that
right, so the rate at which the entropy grows is not directly related to, so it's determined by this minimization. So I have two terms in this minimization. Say the second term was not present at all because I had a product state. Then I would just always pick the value at v equal to 0. So that would correspond to the domain wall going straight down. Okay, but then if I have some initial state which has some volume law entropy with some coefficient, then I get a second term that depends on t in this expression. So I need to minimize over v in those two terms together. So then, based on that, I'll end up selecting some intermediate velocity. But which velocity I get depends on which initial state I had. Yep.
Okay.
Naive, but you map the Lorentzian evolution by into an Euclidean evolution by an operator Pn, P2n. Right?
Yeah.
Do you have any bulk interpretation of that operator, at least for n equals to 1? Or maybe if you have of that operator?
Yeah, so I don't know if that would be an interpretation of that operator itself, but one thing that you can see is that in the n equal to 1 case, you can use it to compute 2-point functions of some operator. In particular, you can take a version of these Brownian models which conserves some charge. Say it conserves like the total z spin or something. So you take all your h alphas to be such that they commute with the total z charge. In that case, if you look at the 2-point function of the charge density, then you should see diffusion. Okay, and that diffusion is encoded in certain low energy modes of this P2 Hamiltonian. And these seem analogous to the quasi-normal modes that you get in holography for, which are like the realization in the bulk of the hydrodynamic modes.
The low-lying spectrum of this P2, Pn, let's say P2.
Yeah, the structure of that could be more generalizable.
But for larger values of n, we don't know, right? I mean,
for larger values of n, we have not identified anything analogous to the quasi-normal modes, but part of what I'm trying to do is understand like what structure those would have. So this seems to be telling us that they would have some gap dispersion relation, and then the order 1 values of the dispersion relation would be important.
Okay, let's thank Shreya again.
Oh,
sorry, excuse me. I missed a question. Where? Loga. Yes. Hi, Loga.
I just wanted to ask, like if you take very simple system, let's say if you just take a harmonic chain, and can you set up this computation of this domain wall kind of thing that you're saying, and has it been done? Is that?
I think you can. So you can make a Brownian version of that. So you mean just some?
Yeah, I just want the harmonic chain to start with. I just want to calculate in some general state how the say third Renyi entropy like evolves in time.
Yeah. So this method would apply to the case where I make the couplings in that random and time dependent.
Okay.
And then that would also map to some Euclidean Hamiltonian, and I can understand its low energy modes. Without introducing that random time dependent coupling, you can probably still do the calculation in some other way.
This domain wall statement would still hold, right? Wouldn't it?
Yeah, there should still be some effective propagation of the domain. So the kinematical statement that the Renyi entropy can be written as a transition amplitude involving the domain wall, that is still true. But then the fact that this u times u star to the n maps to some Euclidean evolution, that will no longer be true. Okay. But it's probably possible to extract some effective Euclidean evolution because we know that the entropy has to, like e to the minus s has to decay exponentially.
Okay.
Yeah.
Okay, thanks.